I'm a senior engineer at the Motor Controls Innovations Group at BorgWarner. And today's session, or my talk about today, I will talk about what we do, what the automotive industry does. So before I go there, how many of the audience we have here are actually in the automotive industry now? I know that everybody's interested in the automotive industry, but how many we have in the automotive industry right now? Okay, we have some few hands. Okay, good. So that gives a good introduction to where I work. I work at BorgWarner. BorgWarner is defined to be an automotive supplier, tier 1 company or tier 1 supplier. So we supply systems, components, and units for the OEMs, for the vehicle manufacturer, the units that I work in, and that will give you an introduction on what the motor controls engineer need to do or need to work on. It have variety of stuff: motor design, motor controls, power electronics, and battery for two different systems and different units. With the Delphi acquisition, we added a wide range of power electronics and application across all the propulsion systems, inside the vehicle and even outside the vehicle in charging. With that, as I said, we can offer the e-motor only, or the controls combined with the power electronics, or the integrated drives module known as IDM in the industry, which is like the eMachine, power electronics, software, driveline, battery charger, and stuff. So our customers, the OEMs, OEMs are the car brands that you see on the road, like GM, Ford, Stellantis, Daimler, Audi, and does that. So any customer in general could buy one of those components or multiple of those components from us. So as I said, we supply, or the tier 1 company in general, and BorgWarner is one of the major ones, supply components, units, and systems to the OEMs. And in the automotive industry, cost is the king, along with reliability and lifetime and everything. But in order to convince the customer to go for a vehicle, one very key factor is the cost. And again, in the industry, they aim for a profit. So yeah, cost is the key. So we aim for mass production. Again, $1 saving in software or in hardware by eliminating a sensor. If you sell the million units, that's like $1 million saving. That's a lot. So a teeny tiny saving here and there, which could be achieved by smarter software or more clever control algorithm, is actually something that you should be aiming for as a controls engineer. Robustness over the wide range of operating conditions. Can be operated in Arizona in very cold weather, or in Indiana, where we're located, or in Michigan in the winter, and the winter here for people who live in Michigan is not so pleasant, as you know. And it should be reliable over the lifetime of the vehicle. No customer will feel happy to be changing the motor or the inverter or the battery before a certain expected lifetime. People want to have the car. It's not like an iPhone or a cell phone that you change every 4 years. You have the car and you're expected to keep the car for a longer time, and you shouldn't be paying a lot for replacing components, and of course lower cost. One other component that as an engineer you should be focusing on is actually the modularization, the modularity. Again, it is hard. You can write the control software as a model-based software or as a C code or whatever from the scratch every time for the customer, but it's highly infeasible. It's highly expensive in time and cost, and in the engineer and number of engineers used for that. So you have to divide that into modulars or modules, and it takes a very high technical skill to define which part can be modularized and be divided, and then how to integrate all of them together. And again, as I said, we sell components to the vehicle. The vehicle will be on the roads. They are expected to perform very well and very convenient in the road. So, and it can be integrated with other components from other suppliers. So they have to pass through the industry standards, AUTOSAR, ASPICE, ISO 26262. I won't go through the details of them. Those are very well known and established standards. Anyone in the automotive industry knows them, and you can access them. So the main factors affecting the decision of the controls engineer are what I mentioned above here. I will go through how we attack those factors by giving few examples. Again, I have limited time, so I will give just some short examples, but the list of examples would take us days to go through. So one of them is the current sensor characteristics. Let me summarize that to you. So of course, you know, in any motor controls, inverter controls, any kind of controls specifically, you need to do the transformation from ABC, alpha, beta to DQ. We all know that, and then all the way back again. You do the rules that's like well established thing. In the automotive industry, and because again we are aiming for profit, we want to use slightly inexpensive sensors, if you must say, than what is used in laboratories. Why is that? Because again, as I said, $1 saving in unit and you sell million units, you will be saving $1 million. So the problem with the inexpensive sensors compared to the laboratory level ones per se, that they will have a different they'll have like a mismatch in the gain and offset characteristics, which means that even a balanced current may be read as unbalanced due to those mismatch in the characteristics. You have one of two choices. The first one is to buy more expensive sensor, which means that you will be producing more expensive unit, which means that you will be losing money or not making profit, or to transfer the problem from the hardware to the software and use the less expensive sensors, and is now the job or the challenge for the motor controls engineer, the power electronics engineer, to compensate for that mismatch, not to give an offset or the scaling error. So as I mentioned here, or the graph show like an unbalanced current, it actually should be balanced. So unbalanced reading in the alpha beta or in the ABC, like the two graphs in the top, should be by control compensation, change it to be a balanced one in the alpha beta and the DQ through controller algorithm. That's one example again of what we do. Another example, a very big important aspect, as Tommy said, and I just touched on that as well, and yeah, that's most of my day is the e-motor and inverter temperature estimation and models for the microcontroller in the inverter and the motor in the vehicle. So basically, thermal temperature or the temperature estimation is a very important factor, and thermal security and stability is a very important factor in the components. Like in a nutshell, component can go bad due to electric stress or thermal stress. That's the end of that's basically how component can get damaged. And when a component got thermal stress, you can work in derating operation, which means that you will not be delivering the required torque or the required current and speed and so on and so on. So an adequate model, a reliable model that use a good thermal estimation or temperature estimation technique for the motor and the inverter, or both of them, or any other component in general, is required from the motor controls or the power electronics engineer. So better temperature estimation model means that you will have lower cost by eliminating the number of thermal, the thermal sensors or the temperature sensors, because again, we want to save money, we will not be throwing sensors all over the inverter and all over the motor. We have to eliminate and estimate some of them. And it will enhance the reliability by reducing the number of sensors, because you have now low number of units or components that can go bad, and actually reduce the cost of warranty, because again, if one sensor means it's like electromechanical or electrothermal component can go bad, you need to replace it, that's like a cost in the warranty. So usually what the teams do in offline, they can develop a great thermal model of, I don't know, 100 thermal nodes or 20 thermal nodes, which will do great job in estimating the temperature. But to put that on a microcontroller in a vehicle, again, we are not using the D-Space with like $10,000 or $5,000. We're using like commercial microcontroller. We want to make the thing reliable and cheap, and inexpensive at the same time. We shouldn't be using the word cheap here. But so there is a trade-off, and this is up to the controls engineer to be using what is the accuracy of the offline model versus the complexity. Like how good is good enough? Like if I get 100% accurate, let's say 99% accurate model, how it will perform versus like an 80% accurate model? How it will perform in the torque accuracy? How it will perform in the protection of the system? Do I need really the 99%? Maybe I need it. Maybe I need like a more capable microcontroller, a more expensive one. Or 80% or 70% accurate model will be good enough. And again, that's like one of the decisions of the motor controls engineer. The last example I will give is modularity. As I mentioned, you can, hypothetically speaking, write the code in model-based or in C, whatever language, from programming language, from scratch for each component, for each project. That will be highly infeasible. You will be out of the market sooner than you expect. It takes a lot of time, it takes a lot of cost, it takes a lot of number of engineers hours. So you should do, or it is feasible or more feasible and functional to use modularization, like to divide the control functions into different modules, and then the question, what go where, what can be modularized, and how to mix and match, how to combine both or some of those. If the customer is buying the inverter only, or the customer is buying the inverter and the motor, or the customer is buying the entire iDM with the drive line, with the software, or with the or only the battery, with the battery charger, how to mix and match between those like a Lego system to put them together. Again, any piece of software or controls that you wrote, it has to be compliant to the industry standard. Like a very known common test is the V-cycles through the automotive. Again, that's available on the internet. I don't want to waste your time on explaining that. And the challenges here for the motor controller, for the power electronics control engineer in the industry, is how to do calibration for each module. The compatibility with lower level abstraction and softwares, how to do the hardware, like the effect of the hardware specific and specifics and projects on that, and of course meeting the industry standards. So in a nutshell, to summarize, the main challenge or the main problem with the motor controls engineer or the power electronics controls engineer is trying to attack here is to enable the hardware teams, the eMachine design and the power electronics team, to use a less expensive component and to transfer the issue or the challenge or the problem from being a hardware related to being a software or controls related, and solve these problems through controls. And that's again required a high set of technical capabilities and understanding of the system, of the motor, of the inverter, and definitely of the controls. And the switching techniques, of course. For that, you are trying to minimize the cost, maximize the performance. Everybody wants to have the greatest vehicle. Again, like Tim was explaining yesterday from GM, that even the vehicle test, if it is towing whatever number of tons, if you will never tow this number of tons, if you know that this vehicle is capable of towing this number of tons, you will still buy it. Like you will be feeling comfortable to have this kind of capable vehicle with you. Enhancing the execution time, you are driving this vehicle in real time, in life, and the worst advertisement to happen to any kind of vehicle is the vehicle to break down on the side of the road. So it has to be reliable, and it has to be fast in execution and have smooth drive. And of course, we are in the industry, so we have to comply to the industry standards, and that is achieved, as I mentioned, between the trade-off between complexity and accuracy. I hope I didn't take a lot of your time, and I hope it was a fruitful discussion, and I'm waiting for your questions and discussions. Thank you.